Alright guys, I want to show you something cool. I'm working on a project that involves using openCV to track the position of the LED. While this may seem simple, the difficult thing is the videos are very noisy and the background um, is not that clean. So how can you get the coordinates of the LED cleanly out of the video? Now this is a bad example of the LED tracker, which was one of the earlier versions. As you can see, I use a mask to filter out the blue light and use the contour to track the position of the LED. But sometimes the reflections of the environment or some noise will cause the mask to not work that well, and it will get these unintended contours. Well, if you just use the contour and the weighted sum to get the if you just use the weighted sum to get the position of the LED, that would be bad because as long as there are noise, um, it will make the coordinates glitchy, it jump around. So what did I do? Well, first let's take a look at the better version. Well, this is the same video. As you can see, there are glitches in the mask, but the tracker is not affected. The tracker is stable as hell. Yeah, it's very stable. So how did I do that? That's what I'm gonna talk about today. Yep, very stable, clean as hell. Well, if we take a look at the code, the most important concept is the tracker circle, which is this circle, this green circle, that has the center, which is the wait a second. Okay, this green circle has the center where the LED is, and basically the it will follow the current position of the LED. This circle can be used uh, as a classifier of where the contours are. For example, if the contours are outside of the circle, it will be treated differently than if the contour is inside the circle. Um, so my logic behind this LED tracker is for the contours that are inside the current tracker circle, that means it is likely not noise. So it will update the tracker circle with a higher weight. So it will change it quicker. But for the contours that are outside of the circle, then it will be updated slower. So as you can see at the start of the video, the tracker moves slowly. But when it enters the LED region, then it snaps onto it and follows the LED relatively fast. So how is this done? The position of the LED tracking circle is calculated using a moving average filter here, where alpha is set to be quite a small number, so it updates very quickly. But if the LED is outside of the circle, then I will calculate a unit vector, which is like no matter where the LED is, no matter where the noise contour is, as long as it's out of the circle, then it will be treated as a unit vector with the same direction, but unified distance, so that the tracking circle will try to follow um, contour outside with a uniform speed. And and this speed can be adjusted by this constant, which I set to 50. That translates to a low speed basically. Um, and for the contours that are inside the circle, it doesn't run this statement, and it is directly added to the total x and y. And I can use it to pass it to the moving average filter, and it will not be a unit vector that is slowed down. That's why this circle moves very slow at the beginning, and when it snaps onto it, it moves quickly. Another thing is you can notice I have a, a yellow circle. The yellow circle is basically where the next frame, where the coordinates of the LED would be in the next frame. And I calculate this using a simple velocity estimator. So I get the last tracker position and the current tracker position. Um, yeah, and I subtract them to get the Vx Vy, and then I add the Vx Vy to the current tracker position to get the predicted tractor position. Well, what do I do with this yellow circle, you may ask? The thing is, if I don't have the yellow circle, when the finger is moving very quickly, there will be a problem because the circle is quite small. If it's big, it's useless. But if it's small like this, and if the finger is moving very quickly, it will misinterpret it as the LED which is moving quickly. Maybe it's going up here and it's here in the next frame. It will misinterpret it as a noise control when actually it's just a very fast moving LED. So the yellow circle is used to determine um, if the LED is actually inside the tracking circle in the next frame to prevent the tracking circle to lag behind too much. Because once the tracking circle detached from the LED completely, it will move very slowly, like in the beginning, and that's not good for tracking, right? We want the tracker to stay on the LED once it has attached to the LED. Oh, there's some other cool stuff, I guess. Yeah, and some other minor details would be I have a state called I have a state called lost track. So lost track is defined as there's no contour inside the tracking circle for n frames. And this n frame is defined by the lost track frame count. I set it to 12. So, and I'm sampling the frames every 4 frames. So basically, for every 3 frames processed, if there are no contours inside the tracking circle, then the last tracking state will be true. And as long as it's not true, um, as long as it's not true, then it will ignore the outsiders. Um, what does this do? I can show you. Okay, okay, here. As you can see, there's one contour here, one contour here. This one is outside of the circle. The tracker is completely not affected by this contour because of how the code is written. Um, so there is a contour inside the tracking circle for the last 3 frames. Therefore, any contours outside of the circle will not affect the the position of the tracking circle in the next frame, which is the moving average filter. So just to recap, I made a LED tracking algorithm with openCV. It uses some moving average filter for the um, for the tracking position, and then it uses a tracking circle that separates contours outside and inside of the tracking circle, so that it will not be disturbed by contours outside of the circle, which is likely noise that easily. So I hope you enjoyed this. I will put the code in the description, probably in GitHub. If you're interested, you can take a look. Yeah. And that's all. Thank you. See ya.